Support vector machines and the kernel trick. So recall our hard margin support vector machine. This was in the first support vector machines video. Our variables are W, this is the ones we want to find to get our classifier algorithm, and our B. And we had linear equations in the variables x sub j and y sub j, and the x sub j and y sub j, of course, given. That's our data. And we introduce slack variables to obtain the primal P of the soft margin support vector machine. So here we're minimizing, but we have slack variables, and that gives us this regularization term, the plus C, sum of the slacks, such that the y sub j f of x sub j is greater or equal to 1 minus the slacks, and the slacks here are greater than or equal to 0. That led to C, our linear support vector machine, where we minimize this objective that has no constraints, and it's a convex objective. What we're going to do now is get a dual form which will allow us to use the kernel trick. And we're going to be using the Krush-Kuhn-Tucker conditions from convex optimization, but don't worry, you don't need them for this course. This will be the only time you ever really have to think of them, and you can just think of them as a generalized set of conditions of setting the derivative equals 0. So here's our soft margin support vector machine from our previous video. And here is the Lagrangian. So the Lagrangian means that we take the constraints and we add these dual variables, the lambda and also the alphas, to go with our constraints. So the slack variables greater or equal to 0 gives us this j equals 1 to m of lambda sub j times slack j, and also the first constraint, y sub j quantity w transpose x sub j plus b greater or equal to 1 minus the slack. Well, we multiply each one of those by an alpha sub j, and combined with our objective, we have the Lagrangian for the soft margin support vector machine. Now, there's a thing called Krush-Kuhn-Tucker stationarity, but that simply means that the derivative of the Lagrangian has to be equal to 0. Well, if I take the derivative of the Lagrangian, then if you look down there, you'll notice that you have a w at the very beginning, a 1/2 w transpose w, and you don't have any other w's until you get to the very last term with the alpha dual variables. So that means we get w minus the sum j equals 1 to n, alpha sub j, y sub j, x sub j has to be equal to 0. We also take the derivative with respect to the slacks. But if you look down there, we have slacks, they're all to the first degree, and they're in the final three sums. So that's going to give me c times the 1 vector, and then minus lambda and minus alpha as vectors. So this is just writing these individual partial derivatives in a vector form. And then we take the derivative with respect to b, but there's only one b in the entire thing, and that's going to imply that the sum, j equals 1 to m of alpha sub j, y sub j has to be equal to 0. Now, complementary slackness. This is a convex problem, so we'll get complementary slackness from the Krush-Kuhn-Tucker conditions. And that says that the lambda sub j times the corresponding slack sub j has to be 0, and the alpha sub j times that boundary constraint condition, 1 minus the slack minus y sub j quantity w transpose x sub j plus b, that product has to be equal to 0. And therefore, at optimality, where we have all these starred variables, we get w star is the sum of alpha sub j star, y sub j, x sub j. But notice this is only when alpha sub j star is greater than 0. So remember, the alpha sub j's here are non-negative, and therefore if they're equal to 0, they don't contribute. And that came from the first KKT stationarity condition. And that means we get support vectors from the fact that when alpha sub j is greater than 0, this quantity in the parentheses has to be equal to 0, and we get y sub I times the quantity w star transpose x sub j plus b star is equal to 1 minus the slack sub j star. So now let's derive the dual function and the dual to the soft margin support vector machine primal. Now I'll just say in advance, there's going to be a lot of symbols that we're going to run into. So the dual is obtained by eliminating W from the Lagrangian using all of our Krush-Kuhn-Tucker results. So here's our stationarity. And notice that we could have written that last vector one as C minus alpha sub j minus lambda sub j equals 0. And here's my Lagrangian. Now, I got to get rid of the W. So notice that our dual is going to be G of lambda alpha with no W's. So how am I going to do that? Well, first we notice that we can collect these three sums and get a C minus lambda sub j minus alpha sub j times the slack j. But notice that the sum of the alpha sub j y sub j's is equal to 0. That means our very last term is going to go to 0. And our C minus lambda sub j minus alpha sub j is equal to 0. And therefore, that term goes to 0. And our W is equal to this sum, alpha sub j y sub j x sub j. So that term is going to become a W sub j. And we're going to get the sum, j equals 1 to n of alpha sub j, minus 1/2 W transpose W. But now we can reuse our stationarity and replace the W by the sum over the alpha sub j y sub j x sub j's. So notice our G of lambda alpha now is in terms of just these alphas. And so this is our dual. Maximize over the alphas, the sum of the alphas minus 1/2 this double sum, alpha sub I, alpha sub j, y sub I, y sub j, x sub I transpose x sub j. But then we also have to use our stationarity for B, and that means we have to require that the sum of the alpha sub j, y sub j's is equal to 0. And we have this condition, we can't leave it out. It's going to say that alpha sub j plus lambda sub j is equal to C, and lambda sub j here is going to have to be greater or equal to 0. That's part of our Lagrangian problem. And that means that the alpha sub j's have to be less than or equal to C. And that gives us our final form. So notice that our dual is actually a function of only the alphas. With our objective, our constraint, the sum equals 0, and the alphas have to be between 0 and our regularization parameter C. And so this is what's known as the dual. It's a support vector quadratic program. Maximize this objective, which is quadratic in the alphas, subject to the sum of the alpha sub j y sub j's is 0, and the alpha sub j's are between 0 and C for all j. So we have to solve the dual for alpha 1, alpha 2, get the optimal values there. Notice that n is the number of features, m is the number of samples, and m tends to be much, much larger than n. And the reason that's important is because complementary slackness actually implies that at most n plus 1 of the very much larger m solutions is equal to 0. If alpha sub j star is greater than 0, then x sub j is a support vector. W star is the solution to the primal, but we can get it from our stationarity conditions with the alpha sub j's that are greater than 0. Our B star we can get in this form. That's just the expression for the constraint function. And that gives us our prediction. Y hat is W star transpose X, whatever our new observation is, plus our B star. And notice that the solution to the dual depends only on inner products. So everything you see defining this process is an inner product. That means we can replace, for example, the xi transpose xj by a kernel. And we can do the same in the soft margin SVM. And we can do the same in the B star. And we can do the same in the prediction. So kernels could be linear, or the polynomial kernel degree D, or a radial basis function, and there are other possibilities. But with any choice of kernel, we first solve the dual to obtain the support vectors. Once you have the support vectors, the W star and the B star can be redefined or can be expressed in terms of those support vectors. And that means the primal solution immediately follows once we know the support vectors. Let's look at an example. Clearly, this data is not linearly separable. A linear kernel, an ordinary inner product, just won't work. But with sufficiently high dimensional kernel, the data can be separated nonlinearly. Here we are using a degree 3 polynomial kernel. And you can see the margin there in gray does indeed separate the positives from the negatives. And the support vectors I've marked here with an X. But remember, this is nonlinear separation, which comes from linear separation in high dimensional vector space projected to lower dimensional data space. So remember, our kernel trick uses this embedding function phi, which tends to be nonlinear. And the support vectors actually define the decision surface, as you can see here. So we often use the support vector machine in association with dimensionality reduction. Often we do some pre-processing, for instance, the principal components analysis, because we can reduce the number of support vectors that are required. So apply the support vector machine to low rank space, maybe using a low degree polynomial. And we often do this with image and computer vision applications, because images are very high dimensional, but they tend to be low rank, and often a relatively few support images suffice, and therefore we can often increase our speed substantially with a little pre-processing and dimensionality reduction in association with our support vector machine. So in summary, support vector machines are quite useful. Just need linearly separable somewhere. The kernel trick is a really good trick. And there are natural extensions to multiple classes. But there are issues. Choosing the right kernel can be very difficult, and it's also a very important choice. And finally, the real world is complex. So we may not have linearly separable somewhere in real world situations.